Hello everybody, this is a presentation on our research project where we studied an eclipsing binary system known as EPIC 2018269668.
Binaries are stars, a system of two stars whose brightness varies periodically as the two components pass one in front of the other. So this is just a diagram of such a system. So you can kind of see the path of the first star, then have the second star, and then kind of right along this line is where you would see those stars passing in front of each other. So one example of an eclipsing binary system is Algol. So there are two stars in that system, Algol A and Algol B, that are orbiting each other, and then this is an actual image of those stars in orbit, and you can see that one of the stars is in front of the other. So with the eclipsing, so what we can do to measure them is we can just take images of them using telescopes, and then we can translate those images into graphs of the brightness of the system, which is also known as flux, with phase, which is essentially the time elapsed since the beginning of the orbit. And then this graph is known as a light curve. So using the light curve, we can translate it to a mathematical model, which then fits the light curve to the model and can give us all sorts of useful information, such as, say, the star's radii, their masses, and the orbital radii, and so on.
So more about our system, as I mentioned, it's known as EPIC 20186968. We found it using the Kepler Eclipsing Binary Catalog, which is a huge catalog that consists of all the eclipsing binary systems that have been found by the Kepler Space Telescope. And the reason we chose our system was because, first and most importantly, it was observable during our time of the year when we were first starting our research project. So to request images on it, we have to be able to observe it in the night sky. And also it had deep primary and secondary eclipses, deep dips in the light curve. Meaning that it would be easier to observe the dips when we were creating our own light curve. And third, it had a very small period error, which would be useful when determining the period later in our research.
So a light curve, as Umar explained earlier, is a plot of basically the brightness versus how far the system is into its period. What we call those flux and phase. So to make a light curve, we organized our data into pairs of phases and fluxes that we gathered with our telescope. And we plotted for each one of our observations, we plotted phase versus flux on this graph. And you can see right here how that graph turned out and how you can see the light curve forming. You can see where the dips in it indicate that the stars passed in front of each other. And then after that, we used two period determination algorithms to see what the period was now and how it had changed since when Kepler observed it. So first we used the standard deviation algorithm, which is also called phase dispersion minimum. So first in that algorithm, we guess a period and we figure out what its phase dispersion is. And we repeat this for a lot of different period guesses, and the lowest phase dispersion we get is the most accurate period guess. So we tie each phase dispersion to each period guess, and whichever has the lowest phase dispersion is the period guess we'll use. And the best period guess we got with that was 0.361740 days. And the other method we can use, which is very similar to the standard deviation algorithm, is the distance method. In this method, we guess a period and find its total distance, the total distance between all of the points. And we repeat this for all of our different period guesses. And the period guess with the lowest total distance is the best guess. And the best period guess we got with that was 0.36172 days. So as you can see, both of the periods we got are very close to each other and to the Kepler period. Thank you.